Good afternoon, students. Today we will continue our discussion of low power VLSI design. Today we will try to cover the fabrication point of view. So, these are the content. So, we will try to cover different fabrication steps, packaging, layout and other discussions. So, if we think about the modern technology, so this is the progress in nanotechnology. Okay. So, few of these, this is still in development phase and mostly in research phase. So, still lot of research is going on. So, it will yet take time to come up as a mature process, but few of these are promising like the spintronic storage, the spintronic devices and nanowires, carbon nanotube. You may have heard few of these. Okay. So, this is the, if you say about the future and the roadmap. So, this is our technology roadmap. Okay. So, you can see that few are research and development. So, if it is advanced technology, it is still in the research domain. Okay. Development is yet to come and established. CMOS is almost, you can say that it is developed and established, and other by CMOS also quite established, and this quantum computing and other techniques, these are yet to come and they are mostly in research domain. So, this is our gate length and how with time the gate length is reduced day by day. So, that helped actually our shrinkage, right, shrinking of the technology or the so that we on the same area we can stuff more number of transistors, right, transistor count will be increased. So, this is a current production, the courtesy is from this paper IDM 09 paper. So, in this figure you can understand that if you talk about the length, okay. So, this is 1.8 volt technology. So, this is a high voltage IO transistor, okay, high voltage transistor, its L is greater than 140 nanometer. Okay. So, as you shrink your device size, dimension, length, so what you can see that its uncertainty, matching, it's all get difficult, right. It's difficult as you shrink the length, so it gets difficult, right. So, this is a low power transistor, this is a low power special type of transistor, LG is 46 nanometer and here the LG is 30 to 34 nanometer. Okay. So, this is a microscopic view. So, we can see the source, drain region, gate region and the underneath channel. Okay. This is even smaller, that is 20 nanometer. So, what you can, this is Intel's 20 nanometer, this is courtesy to B Doyle. So, you can understand that as we are shrinking the length, your control over the device is getting reduced, right. So, all the short channel effects, normally what we see for large channel devices, the current characteristics, they are little bit starting to deviating, right. So, this current characteristic is starting to deviating and it is very difficult to control, right. So, to get the better control, in this case for a very small length, what may happen, the device can have suffer from crosstalk. Okay. Adjacent voltage will introduce noise in your signal. Okay. Whatever is your output signal, if your channel length is starting to getting reduced, it is difficult to have a tight control over the device. When you have a larger channel MOS transistor, you have better control, on and off is very well defined, right. But when you are reducing, you are shrinking your technology, then lots of crosstalks happens. crosstalk means it will be affected by the adjacent signals, okay, that will get coupled, it could falsely turn on for or leakage current that will get more. So, these are the different challenges. So, to overcome that in sub nanometer FinFET technology is preferred. Okay. So, you see this, in this case it is, in previous case it was 20 nanometer, L was 20 nanometer. Now, in MOSFET it is very difficult to have the desired output. As you can see from this current characteristics, the saturation region is, the slope is getting more and more, right. So, to have a better control, the FinFET is a technology where you can see that this source and drain, right, this is your source and this is your drain. Now, the channel is totally surrounded by the gate material. Can you see the difference between the MOSFET? In MOSFET it is, this is your source, this is your drain, your gate is on top of that, right, it is not surrounding the channel, it is grown over. But in case of FinFET, the gate is surrounding your channel, the channel is in between the gate. Okay. So, the control of the gate voltage is better in case of FinFET. FinFET has certain advantages over the MOSFET. In case of particularly in the sub nanometer, FinFET is promising. So, if you all the smaller dimensions, you will be seeing that mostly all the this new technology they use the FinFET. Otherwise, in MOSFET if you go below, then it is very difficult to have the desired characteristics. So, FinFET has certain advantages here, its subthreshold leakage is also improved. So, this is also still under lot of research is going on, but still it is stable. Okay. So, this is our flow, like the system to module, module to gate, gate to circuit, that is schematic, and then device, this is your layout. So, this is actually your layout, this is your schematic oblique, if you are a digital designer you are RTL, this is synthesis actually, here from here you have a RTL coding, okay, and this is your after this you will be having verification, you have the package. So, direct testing. Now, when we have a production, we need to define our how much successful production, right. So, there is one term that is called the die yield. Can you have you heard this term die yield? Huh? So, what is this die yield? This is number of successful ICs, okay, how much percentage is successful, because when you are fabricating some ICs, suppose you are supposed to come up with some product. Now, as you know that fabrication is a costly affair, right. So, the companies they can manage the cost if they have large number of ICs, then they can average out the cost, right, the cost will be divided, right. So, what they try to do, they try to the design is same, it will be just copied to multiple ICs, right. So, so that if they have more number of functioning IC, then your cost will go down, right. So, suppose you are fabricating say 10,000 ICs and almost say 99.9% is successful. So, obviously, your cost will be less, you will be that will total cost will be divided by that number of ICs, right. But suppose your device yield is 80%, obviously, the you have to manage with that much, right. So, your cost per IC will go up, right. So, when we discuss about the cost, there are few variables, one is fixed cost, one is variable cost. Okay. So, for example, the cost of verifications, your setup of your laboratory, these all will come, right, but few costs are there which is not variable. For example, once you set up your laboratory, that is each year you do not need to add up, right, all the instrument you have one time investment. But suppose you need more number of verification engineer, that could vary depending on your project, right. If it is a big project, you need more number. So, these will add up in variable cost and few will be in fixed cost, right. For example, company's overhead, infrastructure, these will be all fixed cost, okay. And variable cost will be, if your number of ICs are changing, that will also vary, okay. And assembly cost, testing cost, verification designer cost, so it will be all variable cost. So, your total cost is cost per IC is variable cost per IC plus the fixed cost by the volume, right. Fixed cost is not variable, but this is variable. So, variable cost per IC plus whatever the fixed cost divided by your total number of ICs. Now, this variable cost, it is dependent on your cost of die. Here comes the die yield. So, if more number of die is working, your variable cost will go down, all right. Here also volume, this is also related to your working volume, right. So, this die yield is the die cost depends upon the number of good die on a wafer and the percentage of those that are functional, okay. So, cost of die is cost of wafer divided by this dies per wafer into die yield, all right. So, these are the factors that will define your cost of your product. Next is few definition that will help us to define our this how this cost of ICs are working, okay, that are set up. This fan out and fan in, I hope you know that last day also we discussed little bit. Suppose this gate is driving say another 4 number of gates, so its fan out is 4. Similarly, suppose this is a 3 input NAND gate, so its fan in is 3. So, what are the number of inputs, that is fan in, what are the number of output it is or number of logic gates it is driving, that is fan out. Now, it is not advisable to have a large fan out, okay. And there is a ideally CMOS it can have it can infinite fan out, but there is a limitation that how much fan out you should have, okay. So, can you tell me why it is not advisable to have large fan out or large fan in? In case of fan out, what will be your problem? Your voltage is fixed, right, 0 to 5 volts say. Not clear, because you are going to a gate, right, you are driving a gate, this is there is no connections, signal strength will be decreased, because what is happening, this is your logic gate and this is your load. If you have more number of fan out, so these cap are coming in parallel, means adding up, getting my point. If you are driving one gate, what are the CGS, what are the C is coming? Can you tell me? See, what it is driving, another MOSFET, this is driving another MOSFET. So, what capacitance it is seeing? CGS and CGD of both NMOS and PMOS, right. So, CGS and CGD of NMOS as well as PMOS, they will all come as a parallel. On top of it, what will be added? The wire will be having some cap, na, right. The connecting wire will be having, if you have more number of gates, more number of wire cap, each of these will add up some cap, each of this gate will add up some cap, right. So, if you have more number, see this will become large. So, you are giving this kind of signal, and if your load is more, what will happen? This square wave will no longer be a square wave, it will become a exponential, right. It will take time to reach, right. So, what will happen? If your load is increasing, this will die down, clear. So, that is why it is advised that do not increase your fan out unnecessarily, okay. Similarly, so actually what is happening, your delay is increased, or your signal strength is decreasing, it may not able to drive. So, large fan out is not advisable. Similarly, large fan in is not advisable. Can you tell me why? See, suppose you are having 3 input, okay. This is your output, can you tell me which gate it is? 3 input, A, B or C, any one is 0, output will be 1. But if you want to get a 0 at the output, A, B and C both has to be 1, right. So, you see A, B, C all should be 1 to get a F is equal to 0, right. Now, can you see that compared to a 2 input NAND gate, a 3 input NAND gate will take more time to 0. Will you agree with this statement? Suppose I have a 2 input, A is equal to 1 and B is equal to 1, then what will happen? Suppose previously output was at 1, so F2 will go to 0, right, 2 input NAND gate, that you agree. Now, you see here what is happening, this signal was previously charged to 1, say previously this was charged to 1. Now, I need to discharge this 1 to 0, right. This discharging will happen through this path, then this path, then this path. So, compared to 2 input, here your path is more. So, your delay will be also more, right. So, what delay? 1 extra RC delay, getting my point. So, this MOS, when this is turned on, what I told you that when this MOS in digital gate is on, it will be on in which mode? Linear mode, right, because linear mode it is resistance is less. In digital I am only cut off and linear. So, linear means this I can replace with a resistance, with a small resistance value R1 value, and this node will have some capacitance value, right. Next, this MOS also I can replace with a resistance and another cap at that node, right. This also I can replace with another resistance and another cap. So, it goes through 3 RC, right, 3 time constant, clear. But if you have a 2 input NAND gate, its 1 to 0 will be, so say this is 3 input NAND and say this is, it will be faster, 2 input will be faster. Is this concept clear? Okay. Same if I say you a 2 input NOR and 3 input NOR, which one will be slower, 1 to 0 or 0 to 1? For NAND, NMOS is in series. So, 0 coming to 0 is slower, right. For NOR opposite thing will happen, going to 1 will be slower, right, because what will happen, P will be in series, whichever is in series I have to go through each of them. Parallel means any one is on, it is on, right. I hope it is clear. So, that is why we do not prefer higher fan in. Higher fan out we do not prefer because our load capacitance was getting bigger and which will cause our dynamic power delay, it will get slower, it will be signal strength will be poor and so on so on. Fan in we do not prefer because our one thing is that it will become asymmetric, my rise time and fall time will become asymmetric, because in one side it is parallel connections, other side it is in series connection, right. So, that is why we do not prefer larger fan in. If you have a chance, you break it, rather than use a 6 input gate, you break it 3 2 input gate, something like that. Okay. Why? Because it will, at the end it will help you in design a low power circuit. So, which may not be seems obvious that why, but these small things will actually build up your design ideas about how you can make a low power circuit. Okay. So, fan out rough examples, TTL gate it can drive 10 approx, ECL gate roughly 25, fan out of CMOS 50, but it is advisable not to go that higher side, although theoretically it is okay, but realistically you limit it. Okay. So, CMOS circuit ideally we have infinite fan out, infinite input impedance, 0 output impedance, infinite gain, but in reality we should limit our fan out. Okay. Now, this waveform I hope you all know. What is this? Voltage transfer characteristics of an inverter. So, this is real or ideal? This is ideal, right. So, why? Because from when input is 0, output is 1, and 1 to 0 it is coming instantly, right, as if like a ideal switch, right. But in reality what will happen? Right, we discussed this last time also. So, this is the zone that we want to avoid as a digital designer, but this is the zone where the analog designer will try to find a linearity. Okay. If you think of this circuit, suppose you have an inverter, this inverter also if you give a very small AC signal that you can amplify, but if you this signal is should be so small, otherwise what will happen? If this is little bigger, you will get a digital signal, you no longer get an amplified signal, you will get a digital signal. So, even this VTC will satisfy the VTC of an amplifier, because in this zone my transistor are in saturation, right. That is why the slope is so high, quickly it will jump, right. But ideally this range is so narrow, it is not suitable, is not it? Getting my point? So, if you are trying to think of an op amp having inverted op amp, like you think of inverting op amp amplifier. So, this zone will be your amplified zone, right. If you recall the op amp, okay, and if this signal is little bit higher, what will happen? Your output will be, it will be clamped, right, saturated, plus and minus VCC. So, characteristic wise it is same. Okay. So, these are few performance, how we define the performance, like the clock high to low, low to high. When we have an input signal and output signal, we generally define the delay from 50% value. We need some reference point, right. Suppose this is my, so what is my delay of this inverter? So, how should we calculate that? We will check what is at the 50% of the input, what is the time. So, this is my time T0, and when for this signal, when my output is occurring, right, this is going from 0 to 1. So, my output will come from 1 to 0, and at the 50% crossing, where is the time at 50% crossing? Say T0, it is T1. So, this is my delay. Okay. So, delay is defined from 50% values. Similarly, rise time I will define from, there is a band, right, 10% band or 5% band. So, if it is a 10% band, so initial value 10% of the initial value to how much time it takes to settle to the 90% of the final value. So, this time will be my rise time. Okay. I hope you all know these definitions. So, these are the RC circuits, exponential waveform, first order RC circuit and its expression. So, this is exponential expression V out is equal to 1 minus e to the power minus t by tau, right. So, this tau is the time constant. So, if your R and C values are getting bigger and bigger, it will take more time, right. Now, from this we can define our energy. Okay. So, the power we can define like the I peak, suppose peak value of the power is I peak into V peak and average value is you make an integration of that and then you find the this PDP delay, this propagation delay and power consumptions. So, this sometimes what happens that this power, if you compare two circuit based on power, so this may not give you the actual idea that which circuit is better. Okay. Suppose two designer, one has designed a circuit which will be work for 10 kilohertz and another has designed a circuit which is working at 1 gigahertz. So, obviously, you can tell that which one will be consuming more power, this one, right. So, if now we compare with a power only, this is not a fair comparison, right, because we are missing another term, that is the time, right. So, power comparisons all times it can be meaningful if both of them are in the same frequency. Otherwise, this is a you can say that this is not a complete or fair comparison. So, that is why we multiply this with time unit, clear. Unless frequency is defined, if you say that okay, both the circuit are working at the same frequency, then you are comparing power, it is fair. But if their frequency of operation is varying, then power is not a fair comparison. Then you either need to come to a PDP or you need to go back to energy, clear. Then you will have to find that which one is consuming less energy, that one is better. Okay. So, similarly like PDP we can have EDP and these are the definitions. So, we will integrate from over the time. So, we multiply with the time, so that we get the energy definitions. So, this is, so all this discussion was little bit about the few metrics like the delay, power, energy, okay, die yield. So, few metrics which will help us to define the cost, functionality of the ICs and which will be used later. Next is we are entering in the fabrication process. So, we will just superficially we will check into what are the different steps of fabrication process and we will try to go through it. So, I hope the basic you all know, we have a crystal, right, silicon crystal which is known as the ingot. You know this process, how this is formed, this crystal ingot is formed. So, we have a molten silicon, right, and then one crystal is just dipped and then slowly it is touched the silicon liquid and one silicon crystal is slowly it is touched the surface and then it is slowly it is moved up and this will form a change the formation of this molten silicon and it will form a crystal across that will form a ingot. Okay. So, this ingot will be formed. Okay. So, this is the first step, you will be having a silicon crystal ingot and then you will cut it into different slices, that will be your wafer. Okay. So, this is your first step, right. Now, you can control your impurity, your all the qualities. Okay. So, these wafer are lightly doped, they have a 10 to 30 centimeter of diameter, thickness of roughly 1 millimeter. They are mostly it is p type, right. Our substrate is, if you recall, substrate is P substrate. If we want to have a PMOS, what we will do? We will make a NOL. So, the wafer should be P type, clear. So, its doping level is 2 into 10 to the power 21 impurities per m cube. Okay. Now, the process of this fabrication is known as the photolithography. Also, I hope that you have a rough idea, right, what is photolithography. So, we use some mask to make this there are some optical mask, and we use some processing step to make a particular structure, right. So, it includes oxidation, etching, deposition, ion implantation, different steps are there which will help us to form the different structure. Okay. So, this technique is known as this technique to accomplish the selective masking called the photolithography. Okay. So, different steps like oxidation, photoresist coating, acid etching, spin, rinse, dry, photoresist removal, etc. will be the different steps. So, this is the graphical view, pictorial view we can say. So, first step is oxidation. Okay. So, at certain room temperature, at certain pressure, you will oxygen will be flowed on over the wafer and it will be oxidized. You can coat some particular chemical which is what it does actually. There are two type of plus and minus type of photoresist. One is transparent to the light, one is opaque to the light, right, that is the process. So, that is certain kind of chemical is used. So, this is the photoresist. Next is whichever portion you want to remove or erase, or that is etch. So, those are etching, chemical etching or dry etching, different type of etching are there. Chemical etching you can understand that some chemical will be go there, and dry etching sometime ion bombardment or something is used. So, to remove the layer. Okay. And then it is clean. If you are using acid, then you need to again rinse it, then clean it, dry it. So, spin, rinse, dry, different techniques are there. Photoresist development, positioning, then maybe some making the surface smooth. So, all of these steps are there, which is all of them in complement, they make us the total photolithographic cycle. Okay. So, this is one example of this fabrication steps. First you have a P substrate, then what you will do? You will oxidize it, right. First step is oxidized. So, one SiO2 layer is grown over on top of that. On top of it you are putting a photoresist. Okay. So, whichever portion you want to remove, so positive and negative photoresist you can do, and then few portion will be exposed and few will be not exposed. So, then you can dope there, right. Whichever portion is exposed, then you can dope some material. Here it is SiO2 is remain and here SiO2 is removed. Okay. So, this is the technique of plus and minus photoresist. So, you do not need to. So, one kind of photoresist, they when you give a light, it will be opaque. Okay. So, few differences are there. So, we do not need to get into the details, you just try to understand the flow, okay, because we are not studying this fabrication in details. So, just overview idea will be sufficient for this course. All right. So, then we need to this photoresist is hardened and then it is removed. So, these are the definitions of those whatever the pictorial view was there, it is the definition of all those steps. So, first one was oxidation layering. So, to deposit a thin layer of SiO2. So, high purity oxygen and hydrogen at approximately 1000 degree centigrade will be flown. Okay. This oxide is an insulation layer and also forms the transistor gate. So, two purpose it is used, one is to form the gate and another sometimes you will be seeing that a barrier. Okay. So, that barrier also that layer is sometime used. Next is photoresist coating, a light sensitive polymer. that is your photoresist, which is thickness is approximately 1 millimeter. This is originally soluble in an organic solvent. So, these are some chemical process. So, when it is exposed to light, making the affected region insoluble, that we were saying that it was hardened. Okay. So, when exposed to light, the photoresist coating will make the region insoluble. So, this type of photoresist is called the negative, and similarly opposite type is known as the positive photoresist. Okay. Next is taper exposure. A glass mask containing the patterns that we want to transfer to the silicon is brought in close proximity to the wafer. Okay. So, this is having all the patterns, whatever is your design, this mask will have this. Okay. The mask is open in the region that we want to process, and so it is just like the our earlier days we had the negative for filming. There were some we have a negative and then we make the photo from that. So, this process is quite similar to that. Okay. So, photoresist development and bake wafer are developed in either an acid or base solution to remove the non-exposed areas of the photoresist. Once exposed photoresist is removed, the wafer is soft baked at a low temperature to harden the remaining photoresist. Okay. Whichever portion is erased, rest of the photoresist to make them hardened, they use some certain temperature, that is known as the soft baked. Acid etching, you understand that certain chemical will be used to remove the photoresist, or sometimes dry etching is also used, okay, where the ion bombardment or other technique are used for the removal of the photoresist. Okay. So, more or less these are the 7 to 8 steps which follows the IC fabrication procedures. Another two important procedures are diffusion and ion implantation. So, we have certain regions, right? We have source region, drain region, right? So, those forming of those regions, they are done using this diffusion and ion implantation techniques. So, in diffusion, the wafers are placed in a quartz tube in a heated furnace, and a gas which you want to dope, right, the type of doping. So, a gas containing the dopant is introduced in the tube. Okay. The high temperature of the furnace typically is 900 degree to 1100 degree centigrade, cause the dopants to diffuse into the exposed surface. Okay. So, in this case of diffusion, what is happening? You have the wafer and you are putting it in a quartz tube, and your gas is flown at certain temperature and pressure, and it will diffuse on the open region. Okay. Which region you do not want to diffuse, that will be coated, okay, hardened coated. Next procedure is ion implantation. In ion implantation, dopants are introduced as ions, okay, into the material. The ion implantation system directs and sweeps beam of purified ions over the semiconductor surface. The acceleration of the ions determines how deep they will be penetrating. Clear? So, previous case it was just a gas, and in ion implantation it will be used as a ion, and certain voltage and electricity will be used to at what is the acceleration of that ionic beam, that will define that how deep you want to go. Okay. So, according to your depth, you will the fabrication designer will decide all those values. Okay. But this ion implantation has some side effects like the lattice damage, it can cause a lattice damage and so many things. So, now you can understand that when we have a, say this is our channel. So, this is our L, right. Now, what was our original L or that we used as a design, and whatever L will be there after the fabrication, there could be a difference, right, that you understand. Why? Because the diffusion, because it is a sub micro range, the control is very subtle, right, and you cannot with 100% you can say that for all the procedure it will be exactly same replica, right. So, this L and this diffusion, they can be grown little bit inside the channel, generally it does, right. So, whatever is your L, they are little bit, that we call the lateral diffusion LD, right. Few portion will be there that will diffuse extra inside the channel. So, your actual length is equal to L minus twice LD, that you all know, and here comes your uncertainty, right. So, you are trying to design a circuit of W by L, but you do not know if you have two device, this uncertainty will cause a mismatch between them. That term mismatch is because of physical implementation uncertainty, uncertainty because of randomness. What are the randomness? One is physical uncertainty between two identical transistor, doping uncertainty, right. Different position may have different doping profile, right, gradient error. So, gradient error will introduce also voltage error also, right. So, all of these will cause a mismatch between two identical transistor, which will introduce error in your design. Okay. For example, suppose this is your wafer, right. So, you can tell that okay, at the corner my variation will be maximum, that you can tell, right. At the boundary my variation will be maximum, and at the center position I can say that they will be more or less similar, that you can tell that at the boundary my variation will be more, at the corner my variation will be more, right. So, one thing is that that is called to have a better matching. What are the technique that we will discuss later, that is called cross coupled common centroid layout technique. Okay. This is a technique that can improve your matching. How should you place, so that suppose you need two transistor to be as much symmetric as possible, but you know that if I place it at one corner, if I place another at this corner. So, as they are at two different gradient, so there will be some difference. Okay. So, there are certain technique, I will touch it little bit, you will be, I think it you will also be introduced in the analog design also about this technique, but I would also like to discuss little bit maybe in later class. Okay. So, all of this lattice damage or this diffusion, that will cause the problems. Okay. These are the sources of the problems. Next is deposition. Now, deposition could be, one is metal deposition, that is for creating the contact, right. You have the, how many deposition are there? Suppose you have a source region. So, from source what you need? Just a connector, right, source pin. Similarly, drain you need a connector. So, what is source? Suppose you have NMOS. What is source type material? N plus, right. So, if you want to have a connection of source, what will be that? That will be a silicon or something else, that connector? that will be metal. So, what kind of contact you need to grow it on top of that silicon? That will be termed as ohmic contact, right. You have heard that, you have studied that about. So, if you have a metal connections on the silicon, they make like a ohmic structure. So, just a connector. So, this connection is bond, clear. So, if you see the, have you seen the layout symbol of the NMOS or PMOS? This kind of structure have you seen? So, this extend is your gate, this is your source and drain are identical. So, anything it could be exchanged. Have you seen that there are some boxes there? So, these boxes are nothing but those metal window, metal contact, those are bonded there as a ohmic contact. This is a top view of your NMOS or PMOS, right. So, if you want to make a connection, what you will do? So, this is generally the lowest metal available. Generally, we have, suppose you have metal 1 and then you will be having higher metal depending on your technology. Some technology has 3 metal, some technology has 5 metal, some technology has 7 metal. So, metal 1, metal 2, metal 3, they generally goes up higher in length, each one is at a particular length. Okay. So, the lowest metal is these windows are lowest metal available, generally M1. So, if you draw a metal 1 connection, this is already, you can say that it is connected to the source. Now, suppose you want to make it to the, sort it to the ground line. So, this is your ground line, clear. So, that is the procedure, and to do that what you need, what procedure you need deposition. So, how we are progressing? You see, we are progressing like first we discussed about what are the different techniques of the fabrications. What are the techniques? Oxidation, photoresist, spin, acid etching, dry, etc., etc. Then how we are doing the diffusion? We are using diffusion and ion implantation. Next step is to make the contact, what we are using? Deposition. Okay. Say for gate, what is the full form of gate? What type of material is used there? Polysilicon. So, you need to deposit that. What is gate? This is a oxide. On top of oxide generally we say poly or polysilicon. This is actually, so we need to coat that material also we need to deposit. Okay. So, these are the different technique so that we can get a connections, right. So, polysilicon on the other hand is deposited using a chemical deposition process. So, this is also deposited, but the process is sometime it is metallic deposition, sometime it is a chemical deposition. Okay. So, some silane gas over the heated wafer coated with SiO2 as a temperature of 650 degree centigrade. The resulting reaction produces a non-crystalline or amorphous material called the polysilicon. To increase the conductivity of the material, the deposition has to be followed by an implantation step. Okay. So, although we call it metal oxide semiconductor, this metal is some amorphous structure, and this is preferred because this is suitable with the SiO2. The binding is better. That is why this poly silicon and little bit of aluminum interconnect is also there. So, these are different technique for deposition. Etching, there could be plasma etching or chemical etching that you can use. Okay. So, not going into details, few acid or some chemical step will be, we do not need to get into the details. This is not our syllabus or not, you do not need to get into details, but you just have the overview, that will be sufficient. As a VLSI designer, you should be having idea of all the steps starting from the fabrication to design. Okay. So, sometime in case of ionic bombardments, this sandblasting kind of technique is also used to this opposite electric charge called rapidly moving plasma, which can go and colloid and remove the. So, this can be also used for etching. Okay. So, acid etching and dry etching, you remember these two term and concept, that is okay. Planarization, that is mechanical or chemical planarization, any rough surface if there is there, that you can remove. So, this is the manufacturing process of the CMOS technology. So, define your active area, each and fill the trenches, implant well regions, deposit and pattern of the polysilicon, implant source and drain, and create contact via windows, deposit and pattern of metal layers. So, whatever we discuss, this is step by step, these are the broadly these are the steps that you will be doing. So, this generation is known as the masking, generating the mask, right, all of this. So, your cost of fabrication actually depends on how much mask you need to generate, okay, if you are and accordingly your fabrication cost will be decided. So, that was an overview about your IC fabrication, and let us discuss little bit about the layout representation. So, that we discussed now, that is this extended version is gate and this is our source and this is our drain. And what I told that there are some window, that window will tell you the that metal deposition actually, right. So, different color are used to help the designer to give a view that okay, this is the different regions, right. So, beneath the gate is your actual active regions, right, the length is known as the active regions, right, and this is your diffusion. So, this is your diffusion region, this is your diffusion, source and drain diffusion, this is your gate region, that is little bit extended, and beneath this is your actual active channel, right, the L, this is your L, right. So, if I draw the 3-dimensional view, so this is my L, this is my source, this is my drain, and this how deep it is, that is your W, clear. So, this is your W. So, when we talk about W and L, this is my L, this is my W. You need to have a 3D. Okay. So, this window is your metal and this is your diffusion. So, depending on NMOS and PMOS, suppose this is NMOS. So, this is your N plus region, N plus doping, this is your N plus doping, and this is your metal 1 connections, clear. Now, suppose I want to convert it to a, or suppose for in PMOS fabrication one extra step you need, what is that? This step is okay, but for PMOS it will be grown over on NOL. So, another region will be covering that, right, and that will be diffused with N plus material, right. So, that NMOS material will be covering that, okay, N type material. We will discuss this in case of PMOS. So, you do not need to worry about that at this moment. Now, are we forgetting anything? Gate is done, source is done, drain is done. Are we forgetting anything? Substrate, because it is a fourth, right, there are 4 gate. So, substrate for NMOS, it is for all, right, common substrate. Suppose you have one NMOS here, another NMOS here, another NMOS here, but substrate P substrate is the common wafer, right, but still we need to give a local connections for all of this substrate, getting my point. Suppose I have 3 NMOS and as a designer you are thinking that okay, I know that substrate is common to all. So, I will give only one contact for the bulk connections. I will give only one contact here and make it ground, but it will give a soft warning. It will tell that this two NMOS, what will happen, can you tell me? This substrate is coming through a resistance, right, because what is substrate material? P doping. P doping is very lightly doped. So, it will have a resistance, right. If it is a highly doped, then its conductivity will be higher, right. Lightly doped means it has some resistance. So, if you do not have any contact here, only this contact is coming to ground. So, this is strongly connected to ground. So, this NMOS is seeing a substrate that is having 0 volt, but this NMOS and this NMOS, their substrate voltage could be higher. Why? Because of this IR drop, right. Some current will flow through the substrate, you know, all the parasitic diode, all the leakage current, that will flow through what? Substrate. This is a, all of these diode, some reverse bias current will flow through them and they will go through which? This resistance and then through to this ground. So, if this substrate connections is not given to all of the NMOS, they will give you some warning that it is not substrate, it not strongly connected to ground, and it may create, first class I told you one problem in CMOS circuit. What was that? Latch up. All the modern technology this is, but you need to provide the substrate connection for all of this MOS. Clear? So, what is this substrate connection? That is known as the P tap. What will be that? Combination of P diffusion and a metal deposition. So, what is this P tap? A P diffusion area, on top of that a metal deposition. That metal deposition is connected to this P diffusion and that P diffusion will be sorted to that P type and it will act as a bulk connections. Just like this metal deposition inside the source and drain, that was also deposition, right. So, similar type of contact is, this is also known as the contact. So, when you will be doing the layout, you will be learning this no more. So, do not worry, I am just giving you the hints, okay, hints about the subject. So, these are the steps. So, this is written, you have to have the gate length, metal rules, poly rules, all of these rules are there and these different colors are showing you different regions. For examples, the green is N diffusion, red is on gate hot coating poly. So, this is poly. This blue color is metal and this box is metal contact, diffusion contact. Okay. So, let us stop today and we will continue on this.